microphone? Okay, I'm very done. Hello. Oh, sorry. Okay, so second talk about the combination of a substructural type system and SSA. Yeah, please.
Hello. Hi, my name is Jad, and today I am going to talk about sound and complete refinement for substructural SSA. So, in particular, what we're going to do is we're going to give a denotational semantics for the SSA, or static single assignment intermediate representation, and then we are going to give a refinement theory for this, for SSA as well. Finally, we're going to prove that our refinement theory is sound and complete with respect to our denotational semantics. Or rather, we're going to sketch how all this is done in the paper since, you know, it's a lot. Let's be a little bit more precise here. So the first thing we're going to do is we're going to give an inductive representation of an SSA program, which here is the variable r. So ignore the gamma and L here. We're going to explain the gamma and leave the L implicit for the purposes of this talk. But the idea is that we have some kind of inductive type system on top of SSA programs. Once we've built our inductive type system on SSA programs, we can use this to inductively define a refinement relation on well-typed SSA programs. We're going to parameterize our refinement relations with a theory, R. And so think of this almost like a very discount version of an MLIR dialect, but the idea is that we can write down quite a bit of different kinds of information into this theory. So in particular, we can include equational information. So for example, the fact that a plus 0 is equal to a. But we can also include refinement information, and this refinement information can be effectful. So for example, here, if we have an undefined behavior effect and unreachable triggers UB, we could say that unreachable can be refined to any other program A. So this is very useful when we're modeling low-level languages, as you know we tend to be doing in SSA land. Right? The other thing that we can have is, going back to effects, we could talk about commutativity between effects. So here we have the information that infinity, that is potentially going into an infinite loop, commutes with itself. So this is why, for example, something like Haskell could have two potentially non-terminating operations swap places. But again, since we have a refinement theory, our commutativity doesn't necessarily need to be two-sided. We can use Lipton's concepts of left movers and right movers. So, for example, undefined behavior is a right mover with respect to all effects, and therefore, in particular, infinite loops. This is reflected by the fact that unreachable followed by loop is the same as unreachable, which refines loop followed by unreachable, which is loop. But in general, we don't want infinite loops to refine into unreachable unless we're doing, you know, something C-style where infinite loops are UB. We like our infinite loops to actually, you know, not terminate instead of cause nasal movements. Those are unpleasant. So the last thing that we can encode in our refinement theory, and potentially the most interesting, is substructurality information. So in particular, our substructurality information is associated with effects. We want to talk about what multiplicity we can associate with an effect. And this multiplicity has a polarity. So these are a bunch of fancy words, so let me give a concrete example. In the positive polarity, that is, we are refining, right? Undefined behavior has unrestricted multiplicity. So all this is saying is that if a variable is used twice and its expression, you know, has potential undefined behavior, then we could duplicate that variable. So, you know, potential UB once is the same as potential UB twice. But on the other hand, if a variable is used no times in the expression, here we just have the null expression, then we could just remove potential UV. It's always safe to eliminate potential UV. On the other hand, for the negative polarity, we have that our multiplicity is irrelevant. So what that means is that it's still safe to duplicate, as we said before, but we can't eliminate. And the reason is very simple. If I have a program which does nothing, it would be quite dangerous to randomly stick UV on the front. So our multiplicity information for effects is directed. Don't worry, I'll give some clearer examples later. It's just a high-level overview. So now, once we have this refinement relation, going back to our original typing derivation from both sides, obviously this satisfies reflexivity, and if R refines R prime, then both sides are well formed. So all the usual syntactic theorems. But we're going to take our derivations here, and we're going to assign them a denotational, and in particular, a categorical semantics. However, we're going to take one step further, and we're actually going to assign our semantics in a poset enriched category. So all that means is that our Hom sets are equipped with a partial order. And when we do this, we get a nice and slick way of representing soundness and completeness. Soundness just means that if R refines R prime, then for every category modeling the theory R, the denotation of R is less than or equal to the denotation of R prime. Whereas completeness says that if all categories modeling R have that property at the bottom, namely that the denotation of R is less than or equal to the denotation of R prime, then it will in fact be derivable that R refines R prime. So this is an interesting property because it shows that our refinement system is in some sense the most powerful refinement system. Anything which can't be derived in a refinement system has at least one model in which this is not true. So this is our high-level kind of contribution. We also provide some cool models to show that this is not just an abstract symbol shuffling game. And in particular, we talk about some interesting side effects, such as release, acquire, weak memory, sequentially consistent concurrency, which is, simpler, but also nice, undefined behavior, and all kinds of other fun stuff. We formalize significant portions of this in Lean, though the whole formalization is not done yet, primarily because I discovered locally nameless. I'm in the process of redoing it because I can't help myself. And we also introduce another language, lambda item, which it turns out is very important for actually getting this mess to work. So that's a slightly more low-level kind of description of what we do in the paper, but a good portion of this audience is probably still lost, and that's because I still haven't answered a particularly important question, which is, of course, what is SSA? So while describing this, I'm going to talk about what SSA is. Consider the following highly complex imperative program written in everyone's favorite imperative language, while. I really don't understand why anyone invented any others. So this program prints the numbers from 0 to n. Not inclusive, of course, as is, right and proper, right? So while is an excellent language. People have been teaching semantics courses about it for the past 10,000 years or so, but we're imagining it's a more complicated imperative language that's hard to do semantics on, and moreover, this is structured control flow. It's not, we don't have a while CPU. I guess WebAssembly counts as a while CPU, maybe, but that has too many features. We want an intermediate representation. So, the most common intermediate representation is just literally doing, taking this and breaking it down into basic blocks. So boink, and these are the basic blocks of our program. So what is a basic block? A basic block is a series of instructions. So that printx is an instruction, and every assignment is an instruction. If we really want to be uniform, we can treat printx as an assignment to a temporary variable we don't use. And then each instruction is followed by a terminator, which tells us where we jump to next. That can be a conditional branch, which jumps to either A or B, or an unconditional branch, which just, jumps somewhere, right? And these basic blocks have labels. So all we do is we take this and we kind of lower it down into unstructured control flow in a mechanical way. This is called the readdress code, or RTL. Now, this intermediate representation is great. Lots of compilers use it, but the problem is that you can't do algebra. So if I want to reason about the value of x, right, we can label all the definitions of x pretty easily. So here you have x0, x2, leaving a gap for x1. But I don't know what value the x takes in, the print statement or in the addition or in the if statement. And the reason I can't just, pick a label here is because it's either going to be x0 if we're coming from the entry block, or it's going to be x2 if we're coming from body. So SSA basically says, okay, write that down. Now, there's two ways to do that. The first is to have a phi instruction whose value changes depending on where we come from in control flow. And the second is to annotate our basic blocks with parameters and then give the value of those parameters at the call site. It turns out these are exactly isomorphic. It just basically where you give the annotations. If you give them at the call site, then you get basic blocks with arguments. If you give them at the callee, then you get phi nodes, and these are exactly isomorphic. It's a syntactic isomorphism. So we're going to use basic blocks with arguments. And the reason why we're going to use basic blocks with arguments is because I'm sitting in a room full of functional programmers. So everyone here is just like, may God preserve us from imperative programs. These are just simple, tail recursive functions. Why don't you just write these as tail recursive functions? And that is the idea of Appel's wonderful paper, SSA is functional programming, which is where all this categorical semantics nonsense starts. So how do we convert this to an actual well-scoped functional program? Well, first off, we need to ask ourselves how this mess is scoped. So let's go do that, right? If we look at the data structure here, the data structure here looks like we have a bunch of basic blocks, which are vectors of operations. Each one defines a variable v, followed by a terminator. And then we have this flat control flow graph that just has the one entry block and then an ordered, or rather unordered map of, labels and basic blocks. So the order of our basic block doesn't matter here, which is nice, but the problem is this is not a nice thing to do induction on. It's a really unpleasant thing to define a type theory on. I did that once in 10,000 lines of lean, and I'm never going to get those months of my life back. So let's not do that again. Let's look at our control flow graph here. So we see that if we want to get here to the loop area, then we need to go through the entry block. And so therefore, any definitions in the entry block are visible in the loop area. On the other hand, we can get to the loop area without going through the body area, namely, the first time. So any definitions in the body area should probably not be visible in the loop area. Similarly, we can get past the body area without ever touching it. So definitions in the body area should not be visible past the end if there's anything past the end. So if we look at our control flow graph, what I've just described to you is a relation which is called dominance. If we draw dominance here, it looks like these red arrows. Now, what is important to note about dominance is that we have this structure called the dominator tree. Namely, it turns out that, ignoring unreachable blocks, because those don't matter and cause suffering, we have the interesting property that there is precisely one block which dominates you and jumps directly to you. That's called your immediate dominator. So this actually gives our graph the structure of a tree. And the nice thing about trees is that we can do induction on trees. So that tells us how to scope our variables. We scope our variables based on the dominator tree. And, this is the core idea of SSA's functional programming. But this doesn't just tell us how to scope our variables. It also tells us how to scope our basic blocks or our functions here. So in particular, if we look at our dominator tree here, I'm now going to swap the contrast here. So, the CFG goes gray, and there's our dominator tree, right? If we look at that, right, we see that if I added, some extra edges from, say, the body to the rest of the function, or the rest of the function to the body, that would not change the dominator tree. Similarly, if I added a thing that jumps from the rest of the function back to the loop, that wouldn't change the dominator tree either, right? Because we still need to go through loop to get to the rest of the function. But on the other hand, if I added a jump straight from the entry node to the rest of the function, that would change the dominator tree, since now there's a new way to get somewhere. So the invariant here is there can't be any new ways to get somewhere. Because if there is a new way to get somewhere, then the dominator tree will be broken. Just to make this more clear, let's say I added another node over here. That doesn't change the rest of the dominator tree. And now, if I added a function from that node to loop, still doesn't change the dominator tree. Everything is good because there's no new way to get through loop without going through entry. So, the relation is preserved. But again, if I jump from there straight to the end, Same thing. There's a new way to get to the end of the function, and dominator tree is broken. So the intuition here is that the subtree rooted at a given point in the dominator tree is obscured. The dominator tree tells us what is visible. We can't jump into the subtree without breaking the dominator tree. Same thing again. The subtree down there is obscured. So if we think of it this way in terms of scoping, what are we doing? We're inserting these little where blocks here. Let's reorient that so we can see that more clearly, so that we can only so that when we enter a scope, when we enter a subtree, any basic blocks in that subtree are only visible from within that subtree. That ensures dominance. And now our variables are just lexically scoped immutable let bindings. So this tells us that SSA is precisely the same thing as, just with a little bit of let floating, these mutually recursive first-order functional programs. And so therefore, this is just a syntactic isomorphism. You can go from one to the other. The dominator tree can be computed in nearly linear time. So now we can try to build our type theory on this inductive representation. And that's great, except that the refinement relation we're going to get is really complicated. It fills up pages and pages and pages of text. And I don't want to explain that refinement relation, considering I've spent 12 minutes talking already. Oh, also, one last thing is we're going to replace those if statements with cases. So usually cases desugar down to if statements and fallible projections. So that is, A plus B can be projected to A and it's undefined behavior if it's B. That's, for example, how Rust does it. But we want to work with cases because we want to be able to support higher level languages like ML, where we don't want to be sprinkling in undefined behavior unnecessarily. So that's just a quick aside. So the idea is that we want to switch our data structure, right, to a slightly nicer data structure, where the idea is that, so our scope here has the ops, the terminator, and the children that we can jump to. And the idea is those children can jump to each other, and you can jump to any of your ancestors and your ancestors' siblings, but what you can't jump to is any of your ancestors' children. So anyway, this is what we have so far. Is we have while, and then while compiles down to RTL, and RTL compiles down to SSA. That's our adventure so far. Now, it turns out that RTL and SSA are in fact isomorphic, because you could just take those SSA arguments and turn them into extra variables. But while and RTL are actually isomorphic by the Bohm-Jacopini theorem, right? So what this really is we have an axis here, structured to unstructured. And again, I don't want to write down the refinement theory for SSA. I've done this. It's horrible. I don't want to do it again, especially not in this presentation. So we want something over here that is structured, but like SSA. But what's the difference between RTL and SSA, right? Because we don't just want to work with while. If we look at RTL, the variables are mutable. If we look at while, the variables are mutable. But if we look at SSA, the variables are immutable. So what's the immutable thing that has structured control flow? Well, why don't we just come up with an expression language for structured control flow? We're going to call it lambda iter. If such an expression language is isomorphic to SSA, which, hint, it will be, so notice we can see how to compile this to SSA pretty simply. Once we give it, it will be obvious. And then compiling SSA back to the expression language is a complicated transformation that is described and proved semantics preserving in the paper. So we're not going to go over that. But the idea is if we have an isomorphism here, we actually have a nice little commutative square of isomorphisms. And I love commutative squares of isomorphisms. Of course, everything will be up to semantics. So yeah, what's this lambda iter? What's this iteration expression language? So, well, it's literally just ye old expression language with iteration. So in particular, we're going to have expressions of type A. Context are going to be a bunch of variables that have types. This is pretty standard, I hope. And similarly, we're going to have a refinement relation on it. And just like before, we're going to parameterize our refinement relation by a theory R. And just like before, we're going to give things a denotational semantics, post-set enriched to so notice that's going to be a morphism from the denotation of gamma to the denotation of A, where the denotation of gamma is just going to be the tensor product of the denotations of all its variables, right? We're going to post-set enrich that, soundness and completeness, and Not here, but later on, if we look at our SSA transformation, we're going to show that that holds if and only if the transformation to SSA holds. And likewise, we're going to have a compilation from SSA back to expressions that is basically going to be the Bohm-Jacopini transform, but lowered down to the SSA world. So going back to our expression language. Well, so our expression language should obviously have variables. So let's add those in. Similarly, it seems useful to have function applications. So let's add those in too. Those are our operations. Very exotic so far, right? We also have a very, very powerful and exotic operator known as the let binding. This implements sequencing. Okay, so far so good. Now for our first weird feature is that we're going to add an effect system to keep track of all our effects. But this is literally the simplest possible effect system in that all our instructions F are tagged with effects. Effects form a partial order. And we're just going to find out basically what is the supremum of all the effects that appear in a, they form a semilattice. We want to find the supremum of all the effects that appear in an expression. So this is just, simplest possible effect system possible. Now, when I said that our sequencing operator was exotic, I meant it was actually exotic in the sense, not in the sense of how it works, but in the sense of the rewrite rules that it can do. See, the usual rewrite rule for a sequencing operator is substitution, but A can be effectful. So general substitution is always well typed, but just because it's well typed does not mean that it has the same semantics. In particular, we are discussing refinements. So we should ask when the substitution is a refinement of the let binding, or the other way around, when the let binding is a refinement of the substitution. What we're asking is whether A can be pushed over and through B, or whether B can be pushed, or whether A can be pulled out of A and merged back together. So notice there's two questions there. The first question is, what is the effect of A, and what is the effect of B? Can we take the effect of A, epsilon, and push it over the effect of B, eta, or vice versa? Can we pull it backwards over the eta? That's our first question. Second question is, how is X used in B? So how often does X appear in B? That's going to be our quantity Q. Now our quantity is going to take values in this fun lattice. It's either used once, linearly, or it's unrestricted, but we're also going to have the option to be used in an affine way or a relevant way. So what does that mean? Well, consider the following case statement. In branch 1, X is used once, but in branch 2, X is used 0 times. So therefore, X in the case statement as a whole is used affinely, since it's used either 0 or 1 times. Likewise, over here, X is used 1 time there, but 2 times there. So it's used relevantly because it's used 1 or 2 times, but it's never used 0 times. And finally, we're going to add one more thing to make things a semilattice, which is where X is used 0 times, we give a distinguished value. So it's just a very, very simple kind of inductive analysis to find out what the quantity of every variable is. Again, we can compute this very, very fast. Once we know that, we want to add 2 conditions to our judgment. So let's start talking about where let, right, is a where let is refined by the substitution. So we're going to talk about the forward direction first. So to do that, the first thing that we need is that epsilon is a right mover with respect to eta. So in other words, that we could take epsilon and push it forwards over eta. And the second is that whatever quantity X is used in, that's something that we can duplicate or fuse epsilon, appropriately with the polarity that we had before. And then we have this. So in this example, maybe A is undefined behavior and X is used arbitrarily, and this will hold. That works. Or maybe A is non-determinism. If A is non-determinism, well, we're allowed to eliminate non-determinism, so X can be used affinely. But on the other hand, we're not allowed to duplicate non-determinism. Non-det is not the same as let X equals non-det XX. So therefore, that would fail. And if we want to do this backwards, we literally just flip that. We go from positive polarity to negative polarity, and everything still works out. That's going to be our directed substitution rule, and that is the second weirdest rule in this entire type theory. So again, it's not that weird. The rest of the rules are profoundly obvious, and explaining them also tells you what our semantics is, because it turns out we're almost directly giving the underlying semantics by our rules, where we're basically giving the free theory. So in particular, we will introduce pairs, we will introduce units, and we will introduce pair destructuring. We'll also introduce a beta operation on pairs, which basically says that in the arbitrary case, the pair let x, y, a, b, c just becomes two let bindings. In particular, we execute A first and then execute B. So pairs are always executed left to right. This, combined with the appropriate eta rule and a few weird kind of shuffle rules, gives our category the structure of a fried category. So what is a fried category? A fried category is a premonoidal category. Now, what is a premonoidal category? It's like a monoidal category, except the morphisms don't necessarily slide over each other. So all that means is that if I have two variables, let's say x and y are both of type nat, and we print x, and then we print y, so those two things are in parallel, but that's not the same as printing y and then printing x. So we don't have the sliding rule, but all the other rules of a monoidal category are still in place. And yet this premonoidal category actually has a Cartesian subcategory, right? It is a wide subcategory, which means it has all the objects, all the types. All our types can be freely duplicated, but it doesn't have all the morphisms. And this Cartesian subcategory is particularly going to be, right, is particularly going to be formed by the morphisms which have bottom effect, or in this case, the terms which have bottom effect, right? So this gives us the structure of a fried category. But we don't just want a fried category. We want to be able to deal with control flow. So let's begin with, a cyclic structured control flow. So we're going to add in injections and abort, and we're going to add in case statements. And we do that, and ta-da, with the appropriate obvious rules, we get coproducts. But there's something more interesting here, which is that we can thread in these gammas into a case statement. So in particular, a gamma so variables gamma appear in both branches of the case statement. And if we fiddle through all the semantics, what we're saying is not only that our category has a coproduct, but that our coproduct is distributive with respect to our premonoidal structure. So all that means is that there's an isomorphism from A tensor B plus C to A tensor B plus A tensor C. And that's just the same as this rule here. So far, everything here has been utterly standard. There's literally only one weird part to this calculus, and that is, of course, our rule for iteration. So bear with me here. Our rule for iteration takes an initial value A. We need to provide an initial value since we actually pass in the state explicitly, right? And then given the current value, which of course starts out at the initial value, that's why it's called initial, right? We execute a body. And the body is going to return a coproduct. In particular, it's either going to return a B, in which case we're done, and we return that B. That's our B there. Or it's going to return an A, and we execute for another loop. So notice, this is none other than a while statement. Actually, it's a do while, if we want to be very precise here. All this is a do while block. If anyone knows what the RVSDG is, we might call this a theta node. All this is a do while block, but we thread through the state explicitly. So it's immutable rather than mutable. And our effect system is exactly the same as before, except we additionally have the constraint that whatever effect we assign an iteration statement must contain non-termination. So we just assume that there's a distinguished non-termination effect here. It's a little bit more subtle in the paper, but that's good enough. Great. And once we've done that, that's a typo. We want to actually give a reduction rule for our resulting thing here. And our reduction rule is going to look a lot like the fixed point rule over here. So the fixed point rule over here just says that, this is one of the rules of what's called an LGOT category. So an LGOT category, specifically a strong LGOT category, is just one of these distributive fried categories equipped with an iteration operator, which is a trace in the coproduct that satisfies this and other equations. So in particular, all this is saying is that F looped in on itself is the same as, executing F. And if we're in the terminating branch, go. If we're in the continue branch, then, that goes into the loop. So it's exactly what we just said before, but translated as a control flow diagram. And if we take this fixed point rule, we can translate it almost directly into a typing rule. So all this says is that we can just unfold the first iteration on the front of an iter. And in particular, the other axioms, such as codiagonal, which looks like that, naturality, which just says that, anything immediately before a break, we could just pull after that break. And codiagonal and naturality are both satisfied. And finally, we have a really weird axiom, which is uniformity. So uniformity says that if H followed by F is the same as G followed by H, or rather, sorry, refines G followed by H with H in the continued branch, then H followed by the iterative F is the same as the iterative G. However, we have to have the condition that the effect of H is a right mover with respect to the effect of F. Otherwise, this will lead to subtle inconsistencies. Now, the intuition behind this is not very complicated. All we're saying is that if we take our iterative F and unfold it into the appropriate infinite tree, we could just apply that single rewrite infinitely many times. So notice, to do this finitely many times, we don't actually need the commutativity condition, but we do need the commutativity condition to do this infinitely many times. That's just how this works. We might be able to weaken it to just commuting with infinity, but I haven't tried yet. And I'm not going to go over the typing rule since we're running out of time. But what this does is that once we prove this semantic sound and complete, we can also give a semantics for SSA in the obvious way by just taking our SSA program's control flow graphs and interpreting those as the semantics. Again, I don't have time to go over that. And we can prove not only that all the arrows up there are semantics preserving, but also that the arrows down into the semantics, so in the case of lambda-ide or Elkhaleq categories, so that's an if and only if by soundness and completeness. Elkhaleq categories are the same as data flow string diagrams over the tensor product and control flow string diagrams over the coproduct. And the Bowman-Jacopini theorem says you only need to nest these one deep, but ask me about that later if you really want to know. And so that's another if and only if. And then that gives us an if and only if with SSA, combined with the fact that, we do have this denotational semantics for SSA. So what we've done is we've actually kind of created a semantic ladder, where the bottom layer of the ladder, it looks like semantics, but what it really is actually a 0.3 representation of the semantics of SSA programs. And now, what's cool about the semantic ladder is you can use it to reason about optimizations, analyses, but most importantly, memory models and side effects at whatever rung of the ladder is convenient. So in particular, it turns out to be, much more simple to do, say, weak memory over an Elkhaleq category land, and through the existence of the ladder, you know that valid SSA optimizations like loop unrolling or distributing things across if statements will work as long as you validate the core rewrites inside your theory. So you might have a rewrite like stuttering, which says that x equals 2 can be refined to just x equals 2. So you just have, that duplicated right goes into 1. And if you just prove that rewrite sound, this theory says that any SSA optimization that uses that rewrite alone is also sound. And yeah. That's what we've done. Sound and complete refinement for SSA through this lambda-ide language and, building up this ladder. Thanks for listening.
Thank you very much. So you might know there's a framework in the compiler community called MLIR.
Yes.
There's a flavor of SSA that I'm going to call hierarchical SSA.
Yes.
That allows basically to have control flow graphs nested inside of operations. So how would you model this in your?
Well, that's excellent. I'm actually working on a model of hierarchical SSA. And so the thing is if you look at MLIR, it's actually a bit more subtle than hierarchical SSA because you have multiple kinds of regions. You have SSA CFG regions, which can be nested. Then you also have graph regions and other nonsense. But let's assume that we only allow what you said, hierarchical SSA, so just nested SSA CFG regions. If you do that, then your operation, so right now we have the simplicity of only basically dealing with binary operations and passing in, a tensor product of things. You can't do that anymore because you want to pass in n regions and you don't want to go higher order, so you actually need n-array operations. Once you do that, the semantics of your operations becomes, and I'm still conjecturing this because I'm working on it, basically a function that takes in one morphism per region parameter and then takes in your operation parameters unchanged. And the only real constraint you have is that this function is continuous with respect to those morphism parameters. So all that means is that, if morphism f refines morphism G, then op F refines op G with, all the other parameters unchanged. And I conjecture that if you have this, you can have a similar kind of free refinement theory for hierarchical SSA, and you could generalize your theory appropriately to do interesting things like pulling operations in and out of hierarchical region. And I'm particularly interested in this because I've started working on weak memory models, as you see. And one cool thing about weak memory models, if you look at like Brooks-style trace monads, is that you can actually talk about the laws of parallelism by having, a parallel composition operator, which naively is a higher order operator. But if you do this, you could have a parallel composition SSA operator and talk about, okay, what are the laws of parallelism here? What's the free model of parallelism? And that's my current future direction of research that hopefully I can jam into the last chapter of my thesis. We'll see.
So for example, in the theorems,
Yeah.
consider